Hello, physics students, and welcome back to another fun day of learning. So today we're talking about something called kinetic energy. Kinetic energy, in short, is the energy of motion. And I know you guys just answered a quick initial check question about kinetic energy, so without further ado, here is my explanation of that question.
All right, here's my explanation for your initial check question. So we had two different scenarios, both balls roughly the same size. One of them is resting on top of a cliff. The other one is in midair. They are both at the same height. So remembering from before, if they are both at the same height, that tells us that they both have roughly equal amounts of potential energy. However, we notice that the ball on the right side is moving towards the ground. It's got a velocity arrow, so it is moving downwards and it has a downward velocity. The other ball does not have any velocity and thus it is not moving. Okay, so this one is not moving. And we want to ask ourselves now, what's the difference between these? The only difference that I'm able to see is the one on the left is not moving and is resting on top of a cliff. The one on the right is moving. It's not, it has no surface to rest on, and thus it is moving towards our ground down here. All right, so the big difference between them is that one is moving and one is not. The one that is moving has kinetic energy. Using my context clues, maybe researching some words, finding out that kinetic has to do with motion. It means that something is moving, and so I am deducing from that that the ball on the right has kinetic energy because it is moving.
All right, so kinetic energy is a little bit simpler than potential energy because there's only one type of kinetic energy. With potential energy, there were different types based on what type of object had the potential energy, and if it was based on like something stretching, if it was based on position, and so different types of forces had different types of potential energy. With kinetic energy, it's simply, is the object in motion or not? Okay, so kinetic energy is going to only be about an object that is in motion. If an object's in motion, it has kinetic energy. If an object is not in motion, it doesn't have kinetic energy. Okay. So now we're going to dive into the equation for kinetic energy. And this equation does get a little bit confusing, so I ask you to bear with me as I go through where it comes from and how we know what it is. So without further ado, here is that.
We are going to be finding the kinetic energy equation. Because energy is something that we cannot measure, but it is something that we can calculate. And it does some pretty cool things with different systems. So the first thing we need to know as we're doing this is that kinetic energy, abbreviated KE, in short, allows objects to do work. So we've kind of briefly discussed this thing called work in our potential energy discussion, but work is not you sitting at your desk typing away at your computer. Work is the ability to give energy to another object, okay? So that's the type of work we're talking about. Work is giving energy to something else. So giving energy to another object. That is this thing called work. All right, so with that in mind, when you are giving energy to an object, you are generally talking about force times how long that force is being applied. So if I was to push in my chair, the energy that the work that I'm doing on that chair, the energy I'm adding to that chair is going to be however much force I'm putting on it and how long that force is there for. Now when I'm talking how long could be time and it could also be distance. There's kind of two ways to discuss how long. When we are talking about work, we are going to pick distance. Earlier, in our previous unit, when we were talking about momentum, that's when time would become important. So, but for energy, we're going to deal with distance, and so we're going to say that kinetic energy is the ability to do work, and work is the force times how long the force is being applied for. That's everything we know. All right, so now what we're going to go ahead and do is we're going to figure out a way to calculate kinetic energy. Now, we could just say kinetic energy is the force times the distance. However, sometimes the object is not giving away its energy, it's keeping its energy, and we want to be able to calculate that energy even when it's being kept and it's not being given away, which means we need to get rid of this force piece, okay? And we know that force equals mass times acceleration, all right? So now let's say that we substitute, instead of force, let's put in mass times acceleration. So our kinetic energy is now mass times acceleration times distance. Now this looks very, very similar to our potential energy equation. Remember, potential energy was mass times the acceleration of gravity times distance. And I want you to notice that similarity, because potential energy, when we're talking about gravitational potential energy, we are talking about we've got an object and we've got the Earth inside of our little bubble. That is our system. If, however, we wanted to say the Earth is no longer in our system and it's just the object, now potential energy becomes the work of gravity. Gravity is now adding energy to our system. However, if we put the Earth back in our system, now no energy is being added, it's still in the system. Okay? So that's why there's that connection. All right, so then we're going to say, well, we've got an equation for kinetic energy, right? Are we good? The answer is no, because when an object has kinetic energy, it is not always accelerating. We could have you in your car driving down the highway, let's say you're going 20 meters per second, and you're not speeding up. Do you still have kinetic energy? Yes. There is still motion. So if there is motion, there is kinetic energy. Okay? So now we need to get the acceleration piece out. And so when we're talking about acceleration, we've got 3 acceleration equations to choose from. Personally, I'm going to pick velocity final squared equals velocity initial squared plus 2AD as the equation that I'm going to solve for acceleration with. However, if we used either of the other two, this would still work out. It would just be a little bit more work. So I'm picking an equation that has acceleration in it. I'm picking one that has distance in it because I've got distance up here. And so I'm trying to have the most amount of similarities as I can. All right. So now we're going to go ahead and solve for that acceleration piece. And when we're doing this, we're going to assume that our objects started from 0. So our initial velocity is going to be 0 meters per second. And we're going to substitute that in and solve for acceleration. So now we've got velocity final squared equals 0 squared plus 2 times my acceleration times my distance. Now we're solving for acceleration, so that means we've got velocity final squared. 0 squared is 0. Anything plus 0 is what we started with, so we can get rid of this. 2AD. To get acceleration all alone, we're going to divide by 2 times d. And so now we end up with, if I take this 2 and I pull it out, that'll be 1/2. We've got that velocity final squared divided by distance equals acceleration. Okay, so now we've got this piece for acceleration. We're going to go back up here, grab this equation and bring it down. KE equals mass times acceleration times distance. I'm just rewriting it down here so that we can see it on our screen. All right, now we are going to go ahead and substitute in our acceleration. Because remember, our objects are not always accelerating when they have kinetic energy. All right, so we substituted that in. Now you'll notice that we have distance on the bottom of the division, and we've also got multiplied by distance. And so those are going to cancel each other out, and we are going to be left with kinetic energy equals 1/2 times mass times velocity final squared. Okay, and since we've only got one velocity in here, we can go ahead and take away that velocity final, and it's just whatever velocity the object is going at that time. It's very important to understand where the equation came from, because we should not just be memorizing equations in this class. We should be really understanding what they mean. And this one tells us that kinetic energy, or the ability of an object to transfer energy to another object, is based on the mass of the object and the velocity of the object at any point in time.
An easy experiment that you could try at home in order to further see the connection between velocity and kinetic energy is an experiment that was first done by Emilie du Châtelet. She was a French scientist in the 1700s. She took a small metal ball and she dropped it onto some clay. And then she doubled the speed of the ball and again dropped it on the clay and observed the difference in the dent made on the clay. She found that as she doubled the speed of the ball, the dent increased in depth by a factor of 4. When she multiplied the speed of the ball by 3, the dent was 9 times deeper. And so she found that no matter what she increased the speed to, the dent was always increased by that number squared. And so that is further shown in that equation that we just derived, that kinetic energy is related to the square of the velocity.